Hey there everyone, welcome back to another video. Today we'll be looking at IGCSE Physics Chapter 4 Turning Effect. Let's start. Moment of a force. So here are three key definitions that we must remember: turning effect, pivot, and moment. You don't have to literally memorize it, but just understand the concept. So what is turning effect? It is when a force causes an object to rotate or would make the object rotate if there was no resistive forces. The pivot. Okay, the pivot is over here. Let me show you the pivot. This is a fixed point above which a lever turns. It is also known as the fulcrum. Yes, the fulcrum moment. It is the turning effect of a force about a pivot, given by force times perpendicular distance from the pivot. We'll talk more about movement as we move further in the video. Okay, let's go down just a second. Yes. Okay, so these are three key things that we must remember. The moment of a force is bigger if the force is bigger. The moment of a force is bigger if it acts further from the pivot. The moment of a force is greatest if it acts at 90 degrees to an object it acts on. So this is 90 degrees. Let's go to balancing a beam. A seesaw is an example of a beam, a long rigid object that is pivoted at a point. The girl's weight is making the beam tip one way. The father's push is making it tip the other way. If the beam is to be balanced, the moment of the two forces must cancel each other out. Okay, so this is what they were saying. The weight of the girl and this is the father's push. The moment of the girl should be equal to the moment of the father for the seesaw to be stable or equal, so that the forces balance out. Let's move on to equilibrium. Equilibrium is when no net force, and no net movement acts on a body. When a beam is balanced, we say it is in equilibrium. When an object is in equilibrium, the forces on it must be balanced, which means there should be no resultant force. The turning effect of the forces on it must also be balanced, so that means no resultant turning effect as well. And when a resultant force acts on an object, it will start to move off in the direction of the resultant force. If there is a resultant turning effect, it will start to rotate. Okay, I think it makes sense. Let's go on to the next question. Next point, calculating moment. Yeah, so this is what we looked at the beginning. Where's moment? Yes, the turning force times perpendicular distance from the pivot. So moment of a force is basically the force times perpendicular distance from the pivot. Okay, let me give you an example. So let's say this is our pivot over here. Sorry for the bad drawing. And then this is our beam. Let's say a force of 20 newtons is applied at a distance of 1 meter. So basically what this says is the force times perpendicular distance from the pivot. So from here to here is the perpendicular distance from the pivot, which is 1 meter, and the force is 20 newtons. So when we multiply 20 coming by 1, we basically get 20. So that will be our moment in the unit on Newton meter, because the Newton times N times M will give us Nm. So I think that makes sense. Let's move on. Now let us consider the unit of moment. Since moment is a force, okay, let me just try and clean this up. Yep. Yep. Now let us consider the unit of moment. Since moment is a force, which is n, multiplied by distance, which is m, its unit is simply Newton meter, nm. Okay, so sometimes the question might give you the distance in centimeters, so you have to change it to meters, or I think, I'm not really sure, you can also write it in Newton centimeters. I have to check that, I'm not really sure, but stick to the Newton meter. Okay, so we have a question over here. Figure 4.7, this is the figure 4.7, shows an example. The 40 Newton force is 2 meters apart from the pivot. The moment of the force equals to 40 newtons times 2, which will give us 80 Newton meter. So this is what I was saying. This is the perpendicular distance, which is 2 meters. And this is our force, 40 newtons. When you multiply this by this, you get 80 Newton meter. Okay, I'm sorry I'm using white, but then hope you can see this. Let's go to balancing moments. The principle of moment states that an object is balanced when clockwise moment is equal to anti-clockwise moment. Let me just write that down. Moment. Okay, I'm sorry for the bad handwriting because I have to use a mouse. We can use the principle to find the value of an unknown force or distance as shown below. Okay, so we have a question over here. The daughter in figure below has a weight of 500 newtons. So let me change this to black and then continue. So yeah, so this becomes 500 newtons and it's sitting 2 meters. So from here to here is 2 meters. The father has a weight of 800 newtons. So here will be 800 newtons. How far to the right of the pivot should he set so that the seesaw is balanced? Okay, so basically what you do is since the unknown value from here to here is x, which is unknown, so we say it's x. Let me change this to white. So we do 500 times 2, which we all know should be 1000 nm. So let's do the same for this side. 800 times x, that will be 800, and that should be 800 nm. So I think where was it? Calculating moment, or wait, let me show you something. Wait, I think I saw something. Just want to add it to what I was saying. Um. Okay, never mind. Okay, yes, over here. You see, anti-clockwise moment is equal to clockwise moment, which means that 1000 nm equals to 800. Oh, by the way, put the x over here. X nm. So you divide both sides by 800 newtons. Cancel the 800 and the newtons. Oh, this 1000. Sorry. All over 800 newtons. So when you divide this, you should get, wait, let me just put it on my calculator. 1000 all divided by, I'm coming, wait, I think it lagged out. Let me use my laptop's calculator. uh CL, uh-huh, 1000, oh shit, coming, uh-huh, 100 divided by 800. Okay, that'll be 1.25. Sorry for delaying. 1.25. Since okay, equals to xm. So since it was distance, it will be m. So the final answer is 1.25 m. Balancing moments, second part. The three children in figure 4.10 have balanced their seesaw. It is an equilibrium. Equilibrium. The weight of the child on the left is tending to turn the seesaw anti-clockwise. So the weight of the child on the left has an anti-clockwise moment. The weight of the two children on the right have clockwise moment. So what this is trying to say here is that the 500 times 2, which is 1000 Newton meter, should be equal, which is the moment on this side, should be equal to the moment on this side. So that will be 400 times 1, which is 400. So whenever there's the other guy over here, you add this plus this because that's the perpendicular distance. That'll be 2 times 3, which is 600, which is equal to 1000. So which makes sense when I say that it's an equilibrium. Okay, let's move on. Okay, yes. So anticlockwise moment equals to 500 times 2000. So 300 times 2. This is the 300 times here and here. 400 times 1. 600 plus 400 will give us 1000. So 1000 equals to 1000. That means it's an equilibrium. More about equilibrium. The diagram below has 5 forces acting on it. These are the 5 forces. First force, second force, third force, fourth force, and the fifth force. So the seesaw is in equilibrium because the upward force balances the 4 downward forces. So whenever you see a question like this, just do that. Since this is going up, up should be equal to down. Just remember this. So 1400 should be equal to, let's do 500 plus 200, 700 plus 400, that'll be 1100 plus 300, that'll be 1400, which makes sense when we say it's an equilibrium. Let's move on to center of gravity. Center of gravity is the point uh, at which the weight of an object appears to be concentrated. Let me just take my white. Okay, so we concentrated. Figure 4.20 shows the position of the center of gravity for several objects. For an object to be stable, it will have a low center of gravity and a wide base. So wide base, this has the most center of gravity. The pyramid is an example of this, yes. So the center of gravity for this watermelon or ball is here. For this cube is here. For our human body, it's in the middle. For a pencil will be here and a table will be here. So this point is where the weight is most concentrated. Finding the center of gravity. Balancing is the clue to finding an object's center of gravity. A meter rule balances at its midpoint, so this is where its center of gravity must lie. The procedure for finding the center of gravity of a more irregular shaped object is shown in figure 2.1. So the keyword here is irregular, not regular. In this case, the object is a piece of card described as a plain lamina. So for all of you who don't know what a lamina is, it's basically a flat two-dimensional shape. Could be like this, but it's like a sheet of paper. It's 2D. The card is suspended from a pin. A plumb line is used to mark a vertical line below the pin. The center of gravity must lie on this. This process is repeated for 2 more pinholes. Now there are 3 lines on the card and the center of gravity must lie on all of them. That is at the point where they interact. Okay, I think I forgot to add the image, but I'll draw it for you. So let's say you take a pin over here, then this is your lamina. Let's say you take a piece of cardboard or you hold it like this, and then you put the pin at this point. So once you put the pin over here, the lamina will move itself and then come to a stable point. Once the thing comes to a stable point, you draw a line from there. You do this again. Next time you do it over here. Okay, so to get the center of gravity, you can do it like twice and get it, but then for it to be more accurate, we do it more than 2 times, like 3 or 4 times. Then once you get it, your thing should look something like this. Sorry for the drawing. Okay, it's not the same thing, but I mean, yeah, it makes sense. There should be something like this. I think it will be like this, and then like this. So you can conclude that this is the point where the center of gravity must be. And I think that'll be all for today. Make sure to stay tuned, subscribe, like, share, and share it with all your friends because I'll be posting questions on this as well. So see you in the next video. Till then, enjoy.